Let's continue the idea of failure investigations. In the previous lecture, we discussed how a Boeing 757 experienced a rupture and it tore an 18 by 7-inch hole over the forward left passenger cabin. In this failure investigation, what was found was that the chemical milling process played a critical role in causing the thickness not being meeting specifications. And so I've also talked about potentially having you download this technical report that goes into the root cause investigation best practices. So, what are the things that we need to do in an investigation? The timeline of events can play a critical role in ensuring that we have a good understanding of what may have transpired in terms of telemetry. Typically, an accident investigation team arrives to the crash site and performs staging, takes pictures, and collects any forensic data. Um, They will label the parts and provide locations of the parts with GPS coordinates. And they may attempt to retrieve flight data recorders and cockpit voice recorders. The parts are later transported to the hangar, and an attempt is then made to puzzle everything together. Inspectors recover and identify the failed components. And what you want to really look at is really get an understanding of, um, very visually, an initial inspection of the components. And you also want to perform a metallurgy examination of the failed components, because if you go through that exercise, you may find failure modes that could point you to the root cause of the failure. You want to match the evidence of the fatigue to the structural loading conditions. Once you receive the components, each item should be methodologically recorded and photographed. You also want to take a macro optical examination, and you want to make sure you identify the failure, and you want to support that with non-destructive evaluation techniques such as dye pen and X-ray. Flight and maintenance history of the aircraft is also gathered along with non-conformances, and it will allow you to understand if there's anything in the history that may not have met the quality controls required uh, for you to be, um, maybe there was an issue earlier in the manufacturing where the thickness was out of spec, and so the non-conformances can help you pinpoint anything that could have gone wrong later. You also want to perform interviews with the pilots. You want to review all the records as well. How is the airplane tracked? Typically, you're going to have a cockpit voice recorder, a flight data recorder. It usually records about 100 hours of data, and it's insulated quite a bit to protect it from impact, fire resistance. In addition, the cockpit voice recorder is capable of recording up to 4 channels of audio, up to 2 hours. What are the methods of inspection that could be quite beneficial in these failure investigations? You're going to have microscopic examination of the failed component. Those are typically done with SEM. And you can also do a qualitative element analysis of features, and you can examine them using SEM by using energy dispersed X-ray analysis, EDX. Other techniques have been used for detailed examination during failure investigations, looking for microstructures, deposits. You also want to make sure that the materials are composed as what you thought. Um, so you can do a spectra analysis to understand what percentage of each material could be in that one metal, for example. Quantitative elemental analysis by electron probe microanalysis is one technique. Orientation imaging microscopy using electron backscattered diffraction is another technique. Phase identification and residual stresses by X-ray diffraction is another technique. Surface analysis of deposits using X-ray photoelectron spectroscopy is another technique. And checks are usually made on the material composition using analytical chemistry techniques, and the metallurgy condition of the material is assessed using both microscopy and mechanical testing. So root cause analysis, there's a few ways to go about this. One method is the 5 whys model. You can also proceed with fishbone diagrams, fault tree analysis, failure modes in effects and analysis. So the why analysis, the idea there is to describe the problem and observations. And once you describe the problem and observations, you want to ask yourself why the problem could have occurred through brainstorming. And that can give you a lot of insights as to what is going on and what could be the contributors. If the root cause of the problem is not achieved, then asking why, again, examining underlying conditions can be very helpful. If the underlying conditions are not explained, then asking why again can also help. So here on the right-hand side, I have a diagram. And what you see here is that something had transpired. And for this event and condition, what I want to ask myself is why? And only if I don't know what's going on. And so then you can look at multiple sub-events that could have caused that event, and then you'll ask why again. And it's possible that for that sub-event, there's multiple sub-events that could explain that sub-event. And so you may want to then look at the underlying issues all the way down. And you may find that when you do that study, you could then determine and identify the root cause. Here's an example of the operation of a tug that's towing a Gulfstream aircraft forward. Suddenly, the tug becomes uncontrollable, which causes the tow hitch to break and extensive damage to the aircraft occurs. And so the question you could ask yourself is, why did this aircraft become damaged? Well, the answer is because the tow bar hit the aircraft. And so then you ask yourself, well, why did the tow bar hit the aircraft? Because the tow hitch broke. And so then you ask the next question, why did the tow hitch break? Well, because the tug was uncontrollable. Well, why was the tug uncontrollable? Because the aircraft was being pulled with a tug rated below 10K, draw pull bar. And so then you ask the question, why was the rating below the minimum specified? Because the tug operator was unaware of the guidance. Well, why wasn't the tug aware of this guidance? Because the tug operator was new and had not been trained on the guidance. Well, why we didn't have the training for that employee? And the answer is because there are no procedures for processing new employees. So you could potentially now identify the root cause by basically putting together a sequence of whys that could take you down to the potential root cause. Here's a 20 whys challenger investigation. And this is a very interesting map. You know, you had a failure event and you're asking yourself, you know, what happened? You know, we had the loss of the crew. So there was impact to safety, impact to the vehicle. We have the loss of the challenger and loss of the crew. So you could go back and start asking those questions. What happened here? You know, the loss of the crew, well, we didn't have a crew module escape system. So, but you also had the issue that the Challenger broke apart. And then you can ask your question, well, why then? So the external tank exploded. So why that? Well, the propellant leaked through the fuel joint. And then you can put evidences along with that as you go, because it will give you a lot of information about what could have transpired in terms of timelines. Then you could ask yourself, well, why did the propellant leak through the fuel joint? Well, because there was an O-ring failure and the combustion gases eroded the O-ring. We call that blow-by. and you have some evidence that points to this. Then you'll ask why, and maybe then now you can go into this branch and say, well, the O-ring failed because the hot pressurized gases inside the SRB, the side rocket booster case, you have some issue there. And then you go back and continue asking those questions all the way back until you could then determine what were the conditions. And in this case, the loss of the O-ring compression, so that you had loss of sealing, was an issue. And so, and you could then bring all the root cause all the way down to the temperature being outside of the tested conditions for the solid rocket motor O-ring. The fishbone diagram is an approach that helps you also determine the condition or the problem. This technique can be very useful because you're examining in a very comprehensive way with no subjectivity. You could evaluate each of the components of the fishbone. In this case, you could have the fishbone typically will have 6 M's. You have the man, the machine, Mother Nature, methods, materials, and measurements. And you're going to have, for each of these, you're going to have issues that belong to this category. So, for example, for men, poor training could be one. For materials, you could be using the wrong grade or the wrong thickness. For methods, that could be the wrong cutter speed. For measurement here, you have uncalibrated instruments. For machines, for example, poorly maintained machines. And then for environments, excessive noise. So these are just examples of what I'm talking about. So the idea of the fishbone diagrams is that it focuses on the cause and not the symptoms. Identify areas that may need further investigation. And this process can be further enhanced using the 5 whys. So the fishbone diagrams can help identify 6 M's that may have contributed to the undesirable condition or problem. So you could then construct an aircraft damage. If there's an aircraft damage, you could construct a fishbone diagram that goes into the various elements. Here, the elements are methods, machine, man, measurements, measures, Mother Nature, and materials. And again, here you will list all the possible things that could contribute to the methods, all the possible things that goes into machine, all the possible things that go into man, and all these things put together will help you then start evaluating each of these bones, and the bones will then be rated. So you rate each bone as most credible, likely, unlikely, and not likely. You definitely want to implement corrective actions for all the bones rated unlikely and above. And you definitely want to basically have a comprehensive fishbone for the failures that could have occurred. In the fishbone diagram, you want to keep in track of where we are in the stages. So you initiate the investigation. You want to determine the sequence of events and the timeline. Then you define the causal factors, and then analyze each of the causal factors. And you are doing that to understand the root cause. And then you analyze each of these root causes and develop and evaluate the corrective actions. By assessing the potential bones, what you're doing is you're helping the investigation team understand where to focus the most. And you don't want to base everything to opinions. You want to make sure you have good factual basis for the assessments. It could be analysis, testing, photos, camera, data. A lot of things can be used to single out an issue. So the Challenger failure is an example of a failure that had, led to the loss of life, and the disintegration of the Challenger was quite significant in the history of space. The trails of the smoke split out. It was like a Y, and those Ys are basically 2 SRBs that were attached. Basically, got detached from the shuttle. In figure 2 here, what you see is the O-ring here. You have the primary O-ring and the secondary O-ring. and the primary O-ring had eroded quite significantly right here. And so you have blow-by. Here's the rocket propellant. You should be familiar with the parts. You should be familiar with the parts of the solid rocket motor at this point. And so this is a shell, this is a propellant, and the hot gases blew by the first O-ring, and the second O-ring was not effective. I did cover this last week, and I would like you to download this paper and go through the Investigational Space Launch Vehicle Catastrophic Failures. It provides a great study when it comes to failure events. So you had the launch, and then 80 seconds later, you lost it. The Challenger model was quite a complex model or design, and it had O-rings near 38 feet in circumference. And the field joints are the ones that leaked. So over here is where you had the leakage. The shuttle was could produce quite a bit of thrust. So the first damage that was really seen is that in less than 1 second, you start to see some amount of smoke. You can see a little bit something there going on that appeared at the ring joint and indicated that the rings are burnt and failed to seal. So less than 1 second after ignition, a puff of smoke appeared right there at the aft joint of the right booster, and that indicated that the O-ring burned through and failed to the seal. And so at this point, the situation did not get any better. The post effects are follows. So you can see here a little bit of heat effects. And so you can see how the timeline events is so helpful, and having telemetry and camera and video evidence is so helpful. On the launch pad, the leak lasted only about 2 seconds. And then apparently kind of went away as the shuttle rose, flying through quite a bit of crosswinds. Then about 58 seconds after ignition, the Challenger was about 6 miles up. And so then you start to have this flicker of flame. You can see that there from that leaky joint. And within seconds, the flame grew and engulfed the fuel tank, which contained liquid hydrogen and liquid oxygen. And so that basically caused the tank to rupture and explode. So, so the shuttle broke up really quickly. Engineers really had all the data they needed. You can see the smoke here. They knew the cold O-rings were likely to fail. That was known. Engineering management believed them and told NASA not to launch. But NASA asked data from the engineers, and those were not presented very well. So NASA was unconvinced, and the engineering and management basically approved for launch. And what is the lesson learned here? So as an engineer, as you work through problems and you're assessing designs, it's important that you be a good communicator, that you can explain why an issue is an issue. If you say that everything is an issue and none of those are real issues, then nobody's going to believe you. But anytime there's a real issue, it's important that you explain and provide very clear understanding of what are the areas to management, explain to them what are the areas that they're looking at a potential risk and why is it. Explain it very well so everybody understands your concerns. Here you can see that the temperature, the Challenger launch was a 32F. And so it's off the charts. And all the incidents, all the flights with no incidents were out here. They had some incidents that did happen, but none of them caused a failure. And so these ones were, the 32F was a complete outlier outside of any flight experience and actually fly outside of testing. The O-rings, they're fuel tank joint, and they are sensitive in the winter, this kind of joints. In mid-1985, scorching became noticeable. And analysis showed that it got worse on colder days. The engineer, Roger Borsjorley, warned superiors, hey, we could lose this flight, for that matter. NASA, in 1985, said, hey, let's not make any changes. I think we're good to go. The night before launch, there was a concern. A lot of people said too cold, delay launch. um, and it was 29F. Every single launch in cold temperatures had showed some amount of damage. And there is competition. We wanted to really look at the Comet Halley, so there was some amount of pressure. The initial scheduled liftoff was not about this time, and there was a delay that pushed the liftoff another day. It got reset on January 25 due to weather, and then postponed another day due to launch processing problems, and then rescheduled again in January 27 due to the weather, delayed again for 24 hours, and then another final 2-hour delay due to hardware interface module problems. And so what went wrong is that the O-ring failed and the flames cut into the main liquid tank. The four more main reasons of the O-ring failure is that you could have pre-flight leak tests, O-ring erosion, joint rotation, low temperatures. These are issues that could go wrong. The risks were managed using critical item lists. So there's, you have criticality 1, loss of life or ship, criticality 2, mission aborted, and then flaws, unreliable or negotiable. In previous missions, criticality 1 issues occurred, but there is no loss of life or ship. Negotiable is identified risk and could later be waived, but there is poor management in this risk management process at NASA. There's known potential problems with O-rings, and O-rings were criticality 1 feature, and O-ring seal failure had been seen on previous missions, and launch had been, there have been constraints placed on subsequent launches. These constraints had been imposed and regularly waived by the solid rocket motor project manager. So the known potential problem, very low ambient temperatures recognized as concern by the contractor to NASA, by Thiokol, and O-ring performance at this temperature was not well understood. NASA officials then pressured Thiokol to withdraw their concerns, and the upper officials at NASA were unaware of these discussions and ignorantly approved the launch. So that's why you had these explosions, because we had a poor risk management process. And on top of that, management was not listening to the engineers that had the data. Now, the engineers may not have done the best job possible to present data in a clear manner, but all of that, is pointing the finger. Bottom line, what is the lesson learned here is if you've tested hardware like a solid rocket motor, flying outside of the range that you tested may not be the best. And this O-ring was affected. It was cold, and so it did not flex. Here you can see the cross section. You have the clevis pen, and this is a good cross section to show you what's going on. Here's the propellant. The propellant is on this side. You have the insulation in blue, and then the skin, the metallic skin, is the one in this color. Then the yellow is your pen. And so your O-rings, the primary O-ring is here, the secondary O-ring is here. So how did this happen? Well, you have the combustion gases on this side where the propellant is. And so then the hot gases start to basically bypass the first O-ring, and then it basically was not sufficient. And so sometimes you may think that the secondary O-ring could be helpful, but in this case, clearly not. So the timeline is straightforward, but the point is that a failure did occur, and you can see a timeline of events here that helped the investigation team understand what happened, and you can see here additional timeline of events. So root causes: the O-ring failed. There was a technical failure. There's previous warnings, untested conditions, and pressure to launch, and miscommunications. So all these things were a major issue that need to be resolved. The ultimate result was a disaster for the shuttle, program, and the Challenger lost $1.7 billion because of this. And then Thiokol also accepted liability and forfeited $10 million. Communication is key. We also want to operate within test conditions, and safety is more important than schedule sometimes, or all the time. We also then, to repeat another failure, the Space Shuttle Columbia re-entering Earth at 10,000 miles an hour disintegrated. All 7 astronauts got killed. The spacecraft, which was $4 billion, got also destroyed. The debris scattered everywhere. NASA ground shuttle was basically grounded by 2.5 years. On February 1, the space shuttle disintegrated during reentry. And following the tragedy, a 13-member Columbia Accident Investigation Board was initiated, and they investigated the incident and identified both the physical and also organizational causes. The board warned that without sweeping changes to address the underlying causes, the scene is set for another accident. And basically what they're looking for is a culture of safety. This incident and its findings offer many lessons that are likely to be applicable to any organization that's involved in high-risk activities. So the physical cause is very simple. The insulating foam separates from the external tank 81 seconds after liftoff. So the foam then strikes the underside of this wing, the left wing here, and breaches the thermal protection system tiles. Superheated air enters the wing during reentry, melting aluminum struts. Aerodynamic stresses destroy the weakened wing, and basically the physical cause leading to the loss of the Columbia and its crew was really breach in the thermal protection system. On the leading edge of the left wing, which was caused by that insulating foam heating and impacting this leading edge, that was caused because the insulated foam separated from the external fuel tank and struck the wing at 81 seconds. And so while the foam is lightweight, when you're moving something at 500 miles an hour, that can be a problem. When you have 500 miles an hour of something like that, foam impacting the wing. The external fuel tank assembly, which includes a cryogenic liquid hydrogen and liquid oxygen tank, is insulated. And it's insulated really to prevent ice formation that could break free during launch and damage the shuttle. But in this case, it was the foam, not the ice, that caused that. And the foam broke away from the left bipod ramp and the strut anchors, and it caused this impact event. During re-entry, the breach in the thermal protection system allowed superheated air to penetrate that left wing where the damage was, and it progressively melted the aluminum structure of the wing. This weakened the structure until the increasing aerodynamic forces caused the failure of the wing, and in essence, you lost the control and breakup of the shuttle. So, it was a flawed decision process in this case. The foam stroke, and it was detected in launch videos. People knew about it. Engineers requested inspection by the crew. Mission managers discounted the foam strike significance. No actions were taken. And during routine reviews on the second day of the mission, video taken during the launch, you could see that foam breaking free. And the external tank and the tank basically had that foam striking the shuttle. And so, unfortunately, you can see a little cloud right there at the moment of impact. Mission technical experts almost immediately became really concerned and assessed the significance of the foam strike. A damage assessment team was formed to study this matter. A series of requests were made for either direct inspection of that wing by astronauts or photographic imagery from U.S. military or other intelligence agencies. But Unfortunately, the shuttle program refused and overruled those requests. The shuttle program management quickly formed an opinion that the formed strike was not safety of a flight issue, and it was mostly, if anything, it could complicate trying to bring Colombia for the next mission. And the opinion was really based in the fact that no formed strikes had caused serious issues in the past. So while technical experts in the engineering ranks were concerned with this, management did not inspect the shuttle. And so, sometimes when you look at the history, history, it can be useful, but when you have these one-off events and you have an issue that could be a risk, it should be mitigated, even if you have great flight experience. The organizational causes here is that NASA received really painful lessons from the Challenger, but it was disturbing that those remained in the Columbia accident. So, what are the key issues? With little corroboration, management had become convinced that a formed strike was not and could not be a concern. And why were serious concerns about integrity of the shuttle raised by experts one day before launch, not acted, in advance? Why had NASA not learned from lessons of the Challenger? The lessons is that space, you need to treat that with humbleness and maintain a sense of um, humbleness and understand that things can go wrong. It's easy to normalize bad issues. So if an issue continues to happen, you basically nothing has happened, so it should be fine, and that could lead to other issues. You want to establish an imperative for safety, perform valid and timely hazard risk assessments, and ensure open and frank communications, and learn and advance the culture. So maintaining a sense of being humble, there were near misses many times. And so it is important to not take future uh, success for granted and to take greater risk. I mean, it's okay to take greater risk, but you want to understand those greater risk and make informed decisions. You also want to make sure you have an organization that's funded on safety and that, we have good understanding of the risk that you are undertaking. Uh, the Fed investigation team determined, and the board determined that NASA had not learned the lessons. Communication was still a problem. There was also this idea of just taking everything for granted. So, what can go wrong? Complacency. Due to our superior safety performance, ineffective risk assessments, reversing the burden of proof, employees are not speaking freely of their safety concerns, business pressures at odds with safety priorities, and failure to learn and apply learnings to improve our culture. Another issue is that the shuttle project staff tried to summarize too important information onto few PowerPoint slides. And so, here's what the report said. When analyses and risk assessments are condensed to fit on a standard form or overhead slide, information is lost and the priority assigned to the information can be easily misrepresented. And so, yeah, if you had an extensive report, perhaps different decisions will have been made. So it's important that anytime you're preparing PowerPoint to convey a message to management, that it be comprehensive, number one. You also want to make sure that it's clear, your message is clear, and the key details are not missed. And here's the damage from the failure modes that occurred. And I also have a final note that I would like you to consider. Appendix F provides personal observations on the reliability of the shuttle by Feynman. And this Appendix F of the Columbia investigation or the Challenger investigation report is a worthwhile read because you can see the pull from management and you can see how people were overstating the fact that the probability of failure was very low. And so observations were made on SRBs and liquid rocket engines in this report that I invite you to look. And so I want to conclude this lecture with a short video that really describes what happens to mission control when people are really concerned. So, and the reason I want to show this and end with that is to remind you that these are real people. In aircraft applications, when you're flying humans to space, you want to take this business with great care. And we talked about that. We want to make sure that all the risks are well assessed, well explained, and then people understand what are the risks that are being undertaken, and that the safety of the culture of safety prevails.